everyone, this is Dr. Diaz and welcome back. Here we're going to talk about bonding, so chemical bonding. In this lesson you're going to learn how and why the atoms get together forming bondings, and through the Lewis structure, how we can predict the molecular properties of the elements, the compound. So have you asked yourself why, for example, they form molecules? Why the atoms get together forming different molecules? And why hydrogen get together with oxygen forming water? So they fall in love with each other. If you know yourself, you know how to answer this question. Let me ask you a question. Why you're here taking class? Why you're in college? Probably some will answer because I love to study. But it's not only this, right? I'm pretty sure that has some more. You're looking for your dream job, or you're looking for a stable future, or you're looking for stability. This is the answer. All the atoms looking for stability. And the stability for atom means where I gonna spend less energy. Where, in which place, with who I gonna spend less potential energy. So if they find some element that can bond together, form a stable compound, they will spend less energy and they are happy and stable. So that is like the most common answer for this question. The answer is always on you. We are made by atoms, so probably you already know all the answers. Just look at the periodic table with more respect and care, and you're gonna start listening, hear the periodic table talking to you. So to understand why bonding theories matter, let's begin with a real world example over here. Medications work because they form specific interactions with biological molecules. These interactions depend on polarity, electronegativity, hydrogen bonding, and molecular geometry. The same bond concept that you're going to learn today here. I brought the example here of the HIV protease. So the HIV protease is essential for the HIV virus to multiply. That's a protein. Scientists design drugs called protease inhibitors by using bonding theory to model the shape of molecules and predict how they interact with protease active site. This shows how understanding chemical bonding can literally save lives. Penicillin, ibuprofen, all other medications are based on this, looking for the bonding theory there. So the bond theories help us to explain how and why atoms attach to form molecules, or also understand why some combinations form stable compounds and why some will not form not stable compounds. They also allows us to predict molecular shapes and the physical and chemical properties of the compounds. Let's start with the Lewis model. One of the simplest and most useful bond theories here is the Lewis model. It focuses on valence electrons. What is the valence electrons? The valence electrons are the electrons located in the last shell of energy in the element, right? Right. And those elements is like the money that you have in your savings, not in savings, in your banking account. In the banking account, you have money that you can use, right, to transfer or spend. The same thing here. The valence electrons are the ones that atoms can transfer or share, okay? So also, the Lewis structure represents that with dots. Yes, with dots around the element symbols, right? So why do atoms bond? Because atoms looking for stability. They form when the potential energy of the bonded atoms is less than the potential energy of the separate atoms. So we have three types of atoms, bonds over here. Non-metal with metals, which is the ionic compounds where electrons are transferred. Remember an example of that? Sodium, for example, they form ions, right? So because sodium will transfer one electron for chlorine over here, chlorine will convert an ion as well. So they have opposite charge, so they attract each other, forming sodium chloride. Covalent, they don't transfer electrons, they share electrons. So it happens between non-metal and non-metal. And we have the metallic, which is metal, and we have electron pool. This is like exactly what the name says. It's like a pool full of electrons dancing around free. This is why metals conduct electricity. So ionic bonds, you already learned a little bit about ionic bonds when you talk about nomenclature, remember? So we talked about nomenclature, we talked about ionic bonds. So ionic bonds are between nonmetals and metals. So metals lose electrons, forming cations. And why they form cations? This is very important over here. So a neutral element has the same number of protons and electrons. So they are balancing each other, right? So, but when they lose electron, what happened? I have more protons than electrons. So now I have more protons than electrons. This is why we have a positive charge, cations. Remember sodium, when it loses electrons, so have more positive than negative charge. So this is why we have positive cations. And metals in group 1 and group 2 has a very low ionization energy, so making relatively easy to remove those electrons. Okay, it's like they are giving away, please take my electron with you. So a non-metal will gain electrons, will not lose, will gain electrons. They have a high ionization energy, so they attract electrons also. Okay, so they have a high electron affinity. So they will attract electrons for itself. So they form anions. And why? Because now negative charge are higher number than positive charge. So now we have a negative charge. So I still have 17 protons on chlorine. However, when it forms chloride, I still have 17 protons, but now I have 18 electrons. Here in the sodium, I have 11 protons and 11 electrons. Now I have 10 electrons and I still have 11 protons, because protons will not change, remember? That is the density of your element. Covalent bonds, nonmetals have a high ionization energy. So instead of transferring electrons, what happened with this ionic? They will share, okay? They share them. So shared electrons lower the potential energy by positioning themselves between the nuclei. So they form a covalent bond. Potential energy is lowest when the electrons are between the nuclei. So metallic bond is exactly the same here. So when I told you the electrons are free, they have a low ionization energy of metals, allow them to lose the electrons easily, okay, like any of the metals that you saw over there. So what happened over here, the metals release their valence electrons in the shear pool. Okay? The simplest theory of metallic bond involves the metal's atoms releasing their valence electrons to be shared as a pole by all the atoms, ions in the metal. Let's try to test your concept over here. Which compound is most likely to contain ionic bonds? Methane, N2O, which one? So the first thing that we need to remember, ionic is metal plus non-metal. So this is a non-metal. This is a non-metal. Non-metal, non-metal. So I know this is a covalent or molecular compound. And here I have a metal. So in here I have a non-metal. So this is our compound, ionic bond. So, and the valence electrons. So we know the valence electrons are held most loosely. Why? because they are far away from the nucleus. Okay, so because they are in the last shell. Imagine if this is the valence electrons over here. Okay, those are core electrons. So they are far away from the nucleus compared to the others. So they are easily to be removed or negotiate those electrons, share. So because of the two previously listed facts, valence electrons are most important in bond. Okay? So when you look at this potassium over here, the valence electrons of the potassium and all the elements in group 1 has just one valence electrons, right? So here is the valence electron. When the potassium transfer this electron, so lose these electrons, this will be the new electron configuration of the ion. And if you look at this, will be exactly like the argon electron configuration, because argon is the noble gas. So that is the octet in previous lab. So it's a complete shell. So it has a 6 plus 2 is 8 electrons. That's octet rule complied. Okay? So to find out the number of valence electrons, you only need to look at the periodic table. So when you look, as I said before, to group 1 is 1 valence electron, group 2 is 2 valence electron. Remember the electron configuration? So all the elements in the group 1 finish in S1. All the elements in group 2, the electron configuration, will end up in S2. And here is S2, P1, S2, P2, until there. So it's easy to find out. Group 70, 7 valence electrons. Group 60, 6 valence electrons. Group 50, 5 valence electrons, and so on. So transitional elements all have 2 valence electrons. And you're going to ask me why. So transitional metals appear to have only 2 valence electrons because the electrons that participate in bonding are the outermost electrons. So in this case, it will be S. So that is the outermost electrons, not the D electrons. Okay? So because they are inner shell, so the D subshell belongs to the previous principal energy level. They are lower energy than electrons in the sublevel S. So I know that you got confused over here because we talk about the oxidation states. That is, the transitional metals has a different oxidation states, like iron 2 or iron 3. Those are different oxidation states. So I know, because transitional metals can use actually D electrons in bonding, which is why they form multiple oxidation states. So this happens because only the electrons that are held in the sublevel S ends, or they are removed, the D electrons become available for bonding. So the 2, let's see here, should be like this. Oh, sorry. The 2 valence electrons that you say is a rule like used in the Lewis theory, and it's perfect for introductory chemistry, but it's really good to know that yes, the electrons in the D sublevel can be used in bonding. Okay, so Lewis structures of atoms, the Lewis symbol of oxygen over here, when you see you have the valence electrons, so we have 6 valence electrons over here, and first we start using 1 dot on each side of the element, okay, like you see here, nitrogen. So we have 1, 2, 3, 4, and then you add the 1 over here. So now I have 5. So you will not do like 1, 2, 3, 4, 5. This is wrong, okay? Also, you do not do carbon like this. It's wrong. If you represent the element with the valence electrons, this is the rules that you need to follow. Okay? So the Lewis bond theory follows the octet rule. So atoms bond because bonding results in a more stable electron configuration. Remember the beginning of this class, I told you atoms look for stability. So they are more stable, they have lower potential energy. And the chemical bond forms by atoms either transferring or sharing electrons. It can be ionic or covalent bonds. Usually, this results in all atoms obtaining an outer shell with 8 electrons. Octet rule, exception. Of course, all the rules has exceptions. Like boron, that can be stable with 6 electrons, or elements in level 3 and down, like 3, 4, 5, 6, and period 3. Period 3, 4. Let's look into the periodic table. It's easy. So 3, 4, 5, 6, 7, all the elements here and down can be stable with more than 8 electrons. Okay, so we have some exceptions. So everything starts with the periodic table and the elements like noble gas. Scientists are looking for the noble gas, looking why they are so stable. And at this point, they start understand why they got together forming bonds. Because they are all looking for stability, all the elements looking to be with the same electron configuration of a noble gas and be stable with a lower potential energy. That's it. That's all. Bye for now.